Welcome to Science Friday number 55.
This week I asked my dad a question. Why does sweat cool you down?
So let's get into it. Well, welcome to Science Friday number 55, everybody. As you see, I have my entire posse here this week, and we're going to talk about states of matter and phase changes between states of matter. But first of all, what are the four states of matter? Go ahead.
Solid, liquid, gas,
Plasma.
There you go, the four states of matter. So this week, once again, we're going to talk about states of matter. And this is, again, part of the series that we're going to do, helping you understand what climate change is all about. In order to do that, we really have to talk a little bit about states of matter and sort of how converting from one state of matter to another, something called a phase change, works in the atmosphere. So the first thing I guess we should do is sort of give an example of each state of matter. Savannah, what's an example of a solid?
ice,
Evelyn, what's an example of a liquid?
water,
Water's a very good example. Rosie, give me an example of a gas if you know one.
fire.
Only from the mouth of Rosie. And finally, MJ, what's an example of a plasma?
Lightning?
Yeah, the lightning channel in air creates a plasma. Very good. So those are the four states of matter, and I think some pretty good examples of each one. What is it that makes a difference between a state of matter? I mean, what is it actually that makes a difference between a solid, a liquid, a gas, or a plasma? Now, the definitions that you've probably heard since early in elementary school, let's see, we've got a, what grade are you in, buddy?
Third.
Got a third grader here. Savannah, what grade are you in?
First grade.
First grade. Avalon, what are you in?
Kindergarten.
Kindergarten. And Roz, what are you in?
Preschool.
Yeah, Head Start. Very good. So we have sort of a smattering of younger kids here. And probably when you were their age, you started hearing about states of matter. And you heard about solids, liquids, gases. You probably didn't hear about plasmas until high school or maybe even college. But what they told you back in the day was that a solid is something that doesn't fit the container you put it in. It has a regular shape, a rigid shape, and unless you do something to it, you beat on it with a hammer or you melt it or do something like that, it's going to maintain that shape. A liquid does something a little bit different. A liquid conforms to whatever container you put it in, but it doesn't completely fill the container unless you put enough liquid in to completely fill the container. So if you put a half a cup of milk into a full cup of milk, it only occupies half the cup. A gas, however, will completely fill any container you put it in. So not only does it assume the shape of the container, but it will completely fill the container. So it doesn't matter how much gas you put into any sort of container, that gas will instantly expand to completely occupy the entire volume of the container. And a plasma is simply a substance that's energetic enough that you start to strip electrons away from their component atoms. So you have sort of these atomic nuclei running around. They're highly ionized. There's a bunch of electrons running around that basically aren't very tightly bound permanently to any one nucleus. So the thing that separates those states of matter in different materials is generally temperatures. Most things are solids at very low temperatures. They become liquids at higher temperatures, gases at higher temperatures still, and then finally they can enter a plasma state if you get to a hot enough temperature. You put enough energy into the system. But those definitions are a little unsatisfying for the purposes that we have now. So we have to come up with a slightly better definition of solid, liquid, gas, and plasma, especially if we're going to talk about atmosphere. Because, for instance, it's entirely possible to find liquid water in clouds that are well below the temperature that you would associate with freezing water, 0 degrees Celsius or 32 degrees Fahrenheit. And the reason for that is those are broad definitions, but the better definition is something called long-range order. And long-range order is a much better way of talking about solids, liquids, gases, and plasma. In a solid, basically, everything is closely bound together. Solids tend to have very long-range order in the atoms and molecules that make up the solids. And as we said the last time, even though in any collection of particles, not every particle has the same energy, the energy distribution in a solid, everything has about the same amount of energy. There's not a huge distribution of energies in most solids. Solids consist of particles, atoms and molecules that are bound together and they have long-range order. There's crystalline solids. Those are real common types of solids. There are also amorphous solids, which don't have a lot of long-range order, but those are more like very viscous liquids. Glass is kind of an example of an amorphous solid. But most solids have long-range order that goes on for a long way. There's a lot of tight binding that goes on between the atoms and molecules. And there's not a huge distribution of energies as a solid. Most of the particles have roughly the same energy. Now you get into a liquid, there's less long-range order. You don't get crystals in liquids, for instance, or at least you don't get great big long chains of crystals all bound together. So in liquids, what you tend to get are a few molecules at a time clumping together. That's what gives water, for instance, its surface tension. So liquids have less long-range order than solids, and that's the best definition of a liquid. You get little clumps of particles that sort of clump together. There's weak bonding, but there's not a lot of huge long-range order. You don't get great big long chains of things that are bound together tightly in any sort of a pure liquid. Now, when you get into a gas, you don't get very much bonding at all. In gases, typically you get particles that aren't bound together. They're all just zipping around. That's why in liquids, they will conform to the shape of the container, but they won't completely expand to fill the container because there's some weak bonding going on between the particles that are in there. In a gas, that weak bonding doesn't exist. Those particles zip around everywhere, and they will impact the walls of the container everywhere because they're free to move in any direction they want to, which means they will exert pressure everywhere, which means they are completely filling the volume of whatever the enclosing container is. In liquids and in gases, as you might expect, it's possible to have a greater distribution of energies than it is in a solid. So as you go up, solids tend to not have a big distribution of energies. Everything is fairly close to whatever the average energy is. When you go up into liquids, the average energy is higher and there's a bigger distribution, a broader distribution, I should say, of energies. When you get into a gas, the energies are even higher. The temperature is higher in most gases, and can be a fairly large distribution of energies in gases. And in a plasma, the temperature is higher still for a given material, and you can have a really big distribution of energy in a lot of plasmas. Now, we're talking in generalizations there, and there's exceptions to all these rules, but we want to keep it relatively simple so that we can increase your comprehension of it. So if you're a physicist watching this and you're pulling your hair out right now going, but wait a minute, I get it. But again, we want to keep this as simple as possible because the ultimate goal here is to help you understand enough about the atmosphere that you can understand what climate change is all about. So we have solids, we've got liquids, we've got gases, and we've got plasmas. Now, whenever you change from one state of matter to the other, that is something known as a phase change. Now, MJ, when you change liquid water into a gas, what's that called? You put a pot of water on the stove, and you turn up the heat way high. What happens to the water?
It evaporates.
It boils, right? And that causes it to evaporate. That's a phase change. You're taking liquid water, converting it to gaseous water, and you have to put quite a bit of heat into it to do it, right?
Yeah.
When we boil water to make pasta, it takes a long time to boil a big pot of water, doesn't it?
Yeah.
And is the burner of the stove really hot? Yeah, it is. It takes quite a bit of energy to accomplish a phase change being put into the system if you're going into the order of increasing the entropy or increasing the randomness, the disorganization of the system. So when you go from a solid to a liquid, for instance, you melt a block of ice, it takes energy to do that. So you have to put energy into a system to increase the disorganization of the system, to increase the entropy, to take it from a solid to a liquid to a gas to a plasma. Those are all processes in which you have to input energy into the system, and it turns out quite a bit of energy. If you look at it mathematically, the amount of energy that it takes, for instance, to take a cup of water from 1 degree, let's say 1 degree Celsius, and you take it all the way up to 100 degrees Celsius, so you're going from where you've just melted it all the way up to where you're about to turn it into a gas, and then you look at the amount of energy it takes to convert it completely from a liquid to a gas. It takes a lot more energy to do that phase change than it does just to increase the temperature within a given phase. So phase changes require a lot of energies to accomplish, but the reverse is also true. If you reverse that phase change, if you go from a plasma back to a gas back to a liquid back to a solid, the system liberates energy. It gives off energy. And that's what's important about understanding the atmosphere, and also in answering MJ's question, why is it that you cool down when you sweat? So what does it take for something to evaporate? Well, if you take a pot of water and just put it out, even without boiling it, if you leave that water out long enough, eventually all the water is going to be gone. Remember, we put water in a big pot for the cat, right? And every few days, even if the cat doesn't drink all the water's gone, right? We got to fill it up again. That's because a lot of that water just evaporates. And you're going, well, what is it that caused it to evaporate? Well, it turns out, even at room temperature, remember, not all of the particles, not all the water molecules in that pot of water are at exactly the same energy. There's a distribution of energies within that pot of water. So at room temperature, 50, 60, 70 degrees, somewhere through there, some of the molecules in that pot of water have enough kinetic energy that they will zip off into space. They'll go from a liquid state where they're sort of loosely bound to other water molecules into a gaseous state. They have enough energy that they will leave the pot of water and go into the air. And it's just room temperature is providing the energy for that. It's not providing enough for the entire pot of water necessarily to go into a phase change all at once, but just in any distribution of particles, they don't all have the same energy. There's a spread of energies, and some of those energies are high enough that those water molecules can escape. That's what evaporation is all about. Now, whenever something evaporates, that requires heat, right? So the reason you sweat is to cool you down in the summertime. Humans have sweat glands. Dogs don't have sweat glands, right? Which is why when you take them outside in the summer, they have to pant an awful lot. That's how they liberate heat.
And they also
Yep, they do anything, but they have to lose heat through their mouth. It's really tough for them to lose heat through their skin because they have fur. Most of them do, and they don't sweat like humans do. We have sweat glands, and what happens is when you sweat and that water gets on your skin and it starts to evaporate, you're going to increasing disorganization, right? You're increasing the entropy of the system. So whenever you take water, liquid water, and convert it to a gas, does that absorb energy or does that release energy?
Release?
No, it's absorbed. It absorbs energy. If it were going the other way, if it were going from a gas back to a liquid, that would release energy. But if it's going from a liquid to a gas, that absorbs energy, right? So if sweat is sitting on your skin, okay, and it turns from a liquid to a gas, it's absorbing energy, right? Where do you think it's absorbing the energy from?
outside.
Outside?
It's absorbing energy from your skin. So it's cooling your skin down. It takes heat energy from your skin to take that liquid water, convert it to gaseous water. That's what cools you down. That's why sweat is a very effective mechanism for cooling you down. That is why you sweat. If you're out on a hot day and you're not sweating, that's bad news because it means that heat stroke is coming on. Now, where this is relevant in the atmosphere is when you talk about these phase changes, remember, one way they absorb energy from a system, the other way they liberate energy back into the system. So let's just consider the atmosphere our system. And let's think about warm air rising on a hot summer day, okay? So we talked last week about the sun shining on the earth. It heats up the earth, and darker patches of earth heat more rapidly than patches that aren't as dark. And that causes these thermal bubbles to form. Now, many of you, if you live in any kind of a mountainous area and you see birds, especially big raptors, you'll watch them try to find darker patches of ground over which to hover, because the thermal updrafts will mean that they don't have to expend very much energy. That warm rising air will kind of keep them buoyant a little bit. It's the same thing with people that fly hang gliders and stuff like that. They look for dark patches of ground because you're going to get more uplift as you fly over those because of all the air that's rising. So the sun shines on a hot summer day, hits a patch of dark ground, heats up that air quite a bit. Most substances, when you heat them up, expand. And that's not universal, but it is the general trend. And there is one notable exception that we're going to talk about in just a second. So you get this bubble of air that expands a little bit because you've heated it up. When it expands, it becomes less dense than the air around it, and therefore more buoyant, so it starts to rise in the atmosphere. Now, we talked about the troposphere, the layer of atmosphere that's closest to the surface of the Earth, a few Science Fridays ago. And we talked about what's known as the lapse rate. It gets cooler as you go up in the troposphere. Do you remember how much cooler it gets, buddy? It's about 5.5 degrees per 1,000 feet, right? So that's on average. Now, that's not everywhere all the time, but on average in the troposphere, where there's not something weird going on like an inversion, the higher you go, the cooler it gets. So as that bubble of air rises, the air around it's getting even cooler, so it becomes even more buoyant. So as this bubble of air rises, it starts to lose a little bit of heat just due to conduction with the air around it and a little bit of convection. Now, at that point, the water vapor that's in that air starts to cool down enough that it will condense into something known as cloud droplets, okay? Cloud droplets are very, very tiny. They're much, much smaller, several orders of magnitude smaller than raindrops, but that's the first step. You get vaporous water condenses in things called cloud droplets, which you can see. They scatter white light. They're Mie scatterers. Now, whenever something goes from a gas back to a liquid, does that absorb energy or release energy?
Release.
It releases energy. Very good. So where does that energy go? Well, it goes into the atmosphere. A lot of the energy that is released into the atmosphere that doesn't come from directly from the sun, that comes from heating the earth somehow, comes from the release of something called latent heat in water. And that turns out to be an incredibly important thing in the atmosphere that we're going to have to spend a lot of time talking about. Now, there is one thing that we talked about a minute ago, and we said that in general, most things expand when you heat them up. There is one really notable exception to that. So most things get bigger as you heat them up, and they get smaller as you cool them down. Is there one really well-known exception to that you guys can think of? What about water? Does water? Yeah. Okay, so what happens to water just before it freezes? Does it get bigger or smaller?
Get smaller.
No, it gets bigger. That's why your pipes will burst if they freeze, right? Water does something a little bit weird. The bond angle changes in the H2O molecule a little bit, and it causes water to actually expand just before it freezes. Now, that exception that water has turns out to be quite fortuitous for life on Earth, because we all evolved from organisms that started out being what are called sessile benthos. They were organisms that lived attached to the bottom of shallow seas. If water did not have that property, then bodies of water would freeze from the bottom up instead of the top down, right? You go out on a river or a lake in the wintertime, it's the top that's frozen, not the bottom. You can generally drill through it and find liquid water underneath. If it were not for the fact that water has this property where it expands a little bit just above its freezing point, then lakes and rivers would freeze from the bottom to the top up. So would oceans if they froze. It would be really tough for life to evolve on this planet as it did. Well, that's enough for the day. I got the whole posse here, and they've been really good sitting still. So let's just do a little recap here. 4 states of matter. What's the first one, Savannah?
Solid.
Liquid.
Gas and
Plasma.
plasma. What is an example of a solid?
Ice.
What is an example of a liquid?
Water.
What is an example of a gas? Don't say it. Say tutor.
Fire.
Oh, you're so naughty.
always
Now,
say that.
I got to make these things PG-13 now on account of you. And what's the example of a plasma, buddy?
Lightning.
A lightning bolt. Now, when you were increasing the disorder in a substance, like when you're going from liquid water to gaseous water, which increases the disorder, does that absorb energy or does that liberate energy from the system around it? It absorbs. If you're going in the opposite direction, if you're going from gaseous water back to liquid water, does it absorb or liberate energy?
Absorb.
It liberates if you're going the other way. Okay.
Know what you're saying.
That's okay. It's not the easiest concept. So then one last thing. Most things get bigger the hotter they get, and they get smaller the colder they get. What's the one exception to that?
Water.
Water's a one. There are other exceptions. There's some metals that do kind of funny things to it in certain temperature regimes. But in general, water is the one notable exception to that rule, because when you cool water down just above its freezing point, it starts to expand, which is why your pipes will burst if they freeze. All right, everybody, that's it for Science Friday number 55. Can you all say bye-bye?
Bye.
All right, we'll see you next week. Thanks for joining us. Cheers.